Hey, this is Mr. Ayton. This is pre-calculus or calculus. We're going to be talking about continuity at a point. So this is our limits chapter, and we're talking about continuous and discontinuity and jump discontinuities, removal discontinuities, and asymptote discontinuities, and all kinds of continuities. So today we're going to take a look at how we can be continuous at a point. And so let's get going. Something that we got to keep in mind anytime we talk about something being continuous, we got to talk about those three conditions. What were those three conditions that we talked about in our previous video? Was that we have to have this f of c, this point, must be defined, right? It must be defined, number one. Number two is that the limit as x approaches c from the left and the right of this function, it must exist. That was number two, which the last and most important thing is that the limit as x approaches c of our function has to be equal to the exact point when we plug it in right there, that defined point. So that has to be true in order for our function to be continuous. If it's not true, then it is not going to be continuous. So here you can see we have a piecewise function. We have c, which is some constant, x squared plus 3, and that's going to be good for every single point less than 3. And then we have x cubed minus cx squared, and that's going to be for every point equal to and greater than 3. And I graphed this, I took the liberties of graphing this on GeoGebra, and you can see right around x is equal to 3, you can see they are not continuous. This green line and this blue line go in different directions, but that was when my constant is equal to 1. And so we're trying to figure out what does c have to be in order for the functions, these two functions have to be continuous, which means the limit has to exist at that exact point. And so what we're going to do is we're going to take this first function, this cx squared plus 3, and we're going to plug in my number right there. So I plug in 3 squared plus 3, okay? And that is going to give me 9c plus 3. Now, anytime I tutor students on this or even teach students on this, they kind of don't like what I just did because every teacher has told them if x is less than 3, it can't equal 3. Remember, we have to go back to what we're thinking in terms of limits. We're taking a look at as the limit approaches this 3. And so that's why I plugged this 3 value in. Now we go to the second function and we're going to plug 3 in. So we have 3 cubed minus c times 3 squared. And so we get 3 cubed is 27 minus 9c. So you can see I'm going to do a little bit of algebra here. I have 18c. I added that 9c on this side. I subtracted 3 and I get 24, which means c has to be 24 over 18 or 4 over 3. And so what I need to do is I need to change my constant, okay? I'm going to put right here 4/3. That changed my function a little bit. And I'm going to put right here 4/3, and that changed my function right here. And take a look at this value. I'm going to zoom in. At 3, you can see we are equal to 15. And so this green function is coming this way, and then it would split at this point and continue and be continuous into this blue function right here. And so that made my two functions continuous. That made my limits exist. That made my limits converge on the exact same point, and the limit equaled that point. So we take a look at another problem. Here, this problem, we have one function. We're not trying to make these continuous. We're trying to see if this is continuous or not. So what are we going to do? We're going to plug in this 5 point right here. Okay, so we're going to plug in that point for x. So we have 5 squared plus 3. So we have 5 squared plus 3. And what are we going to do on the next one? We're going to be negative 10 times 5 plus 28. So let's do a little bit of math here. 5 squared is 25, so we have negative 25 plus 3 is negative 22. We have negative 5 times 10, that's negative 50, plus 28, that's negative 22. Guess what? The limit, as we approached 5 from both sides, from the left side and the right side, from the left side and the right side, we were approaching negative 22. What do we see when we plug those points in? We also hit 22. And so I graphed these out at On GeoGebra, here's the one function in green, that negative x squared plus 3. This blue function, this negative 10x plus 25. And remember, we were taking a look at what's going to happen when we hit equal to 5. And so you can see right down at 5, negative 22, my functions overlay with each other, and they intersect at negative 5, 22. So these functions would be, from the left side and right side, continuous. Let's go through one more problem here. We have a piecewise function. We have two functions right here, and we have x is less than 2, so we're coming from the left side, approaching 2. We're coming from the right side, approaching 2. So let's plug 2 in. So we have 2 squared sine of 2 pi, and we're going to set that equal to 2 squared plus c, that's my constant, times 2 minus 18. So I have 4 sine of 2 pi is equal to 4 minus 18. I have 2c. 4 minus 18 is negative 14. And what do I know sine of 2 pi is? Remember, 2 pi is 0 degrees. What's my y, or my sine, is equal to 0. So that's all equal to 0. So 0 equals 2c minus 14. You can already see what c has to be. C has to be positive 7 for these functions to be continuous. So, hope that helped. Make sure you go to MrEaton.com, do your self-assessment on continuity at a point. Catch ya.